Welcome back, literature fans. Today I wish to tie up some loose ends. I want to talk about box operators and in particular how they are inverse. They have this inverse property. And so let's look at this situation. There's a curve, y equals x to the n, ordinary curve, n equals 1, 2, 3, 4, etc. And it looks like this. And we start at 0. And we go to some point like this, point P, which could be anywhere along this line, and we just draw a box. Then we draw a diagonal. Right? And point P has a parametric form that could be x to the n, right? The x value, well, that's your x, right? And that's the run, or the base. And the height, or the rise, is x to the n, because you plug in x and you get x to the n. See it? Not bad. And so what we can say is that the box of x to the n is equal to x to the n times x. And that looks like a box, right? You got rise times run. Well, that equals x to the n plus 1. Pretty simple. That's the box operator. The box of x to the n is this. It's an operator. It takes a function, transforms it, then returns another function. Namely, 1 power higher, right? Pretty simple. What about the diagonal? This diag of x to the n, well, that equals x to the n. Instead of multiply, now you divide by x. Right? And that looks like the diagonal. You see it? Literally, it looks that way. And that simply equals x to the n minus 1. Notice that from a geometric perspective, the box, well, that's the area, that's the box. And the diagonal is the diagonal slope. And they look kind of different. You say, well, you know, areas and slopes, they're completely unrelated. But in the algebraic setting, in algebra, it's just x plus 1 for the box and x minus 1 for the diagonal. That's the function. And notice, you start out with x to the n and you end up with x to the minus n for the diagonal. For the box, you start out with x to the n and you end up with x to the n plus 1. One more. So let's look at how these are inverse operations. What if you said the box of the diag of x to the n? Right? You can do that, right? So that equals the box. What's the diag of x to the n? Well, that's x to the n minus 1, right? It's this thing. You plug that in. But now, take the box of this thing, and that means raise it by 1 power, right? You see it? You start with x minus 1, and now that equals x minus 1 plus 1, so you're back to the x to the n. And so notice, they're inverse as far as you started out with this thing, and you end up with this same function. And also, the inverse is true. The diag of the box of x to the n, well, that equals the diag of, what's the box of x to the n? That's x to the n plus 1, right? Plus 1. See, it raised by 1 power. But now diag is going to lower it by 1 power. So that again equals x to the n. So you start out again with the same curve. So they're inverse operators. And they're similar to inverse functions. Let's look at inverse function. Let's say that you have, let's say you have y equals mx. That's this one. Or f of x equals mx. And then let's say you have another function called g of x equals, instead of mx, it'll be 1 over mx. See that inverse? The slope here is m, the slope here is 1 over m. And so what happens if you take the f of the g of x? Well, that equals the f of the 1 over mx. But f of x is m, so you got m times 1 over mx, and so that equals x. See how you end up with the original variable x? It's an inverse function. And the same thing happens the other way around. The g of the f of x, well, that equals the g of the, and f of x is mx. Well, that equals 1 over m times mx, right? M cancels m, so that equals x. So you back up to where you start. That's an inverse function. And this also works true for curves like, you can have f of x equals x squared, and g of x equals the square root of x. You see how these are inverses? If you take the square root of x squared, that equals x, right? You're back to the original x. What if you take the square of the square root of x? Well, that also equals x, no matter where you are. So they're inverse. But notice, these are inverse in terms of the variable x. Our box operators are inverses in terms of the curve x to the n. So we're not talking about x, we're talking about the curve or the function x to the n. So it's kind of there's similarity, but there are differences. Okay? But they are inverse. And that's a good thing to know. Okay? And then how does this relate to our signed area and our slope? Remember, our signed area would be the area right here, then this wedge. And the tangent slope, it will be the tangent slope at point P. And remember, this point P can be anywhere along here. So, what is that? Well, the signed area of x to the n, well, guess what? That equals k sub n times our box, right? X to the n times x. And we know that k sub n is 1 over n plus 1. We found that out. So that equals x to the n plus 1 over n plus 1. This is Cavalieri's famous formula. And notice how it's related to the box. It itself is a box operator with this invariant k sub n, which is, there's only one value for a particular n, and it's the same. That's why it's the same no matter where you are. Let's say you're over here or here. It doesn't matter. The ratio stays constant. And so the sine area of this wedge is this k sub n, which is 1 over n plus 1 times x to the n plus 1. And also the diagonal, the tangent slope, which we call the d of x to the n, and that's this slope here. Well, that's simply c sub n times x to the n divided by x. And that's your box operator right here. And c sub n, we found out that it was simply n. So we're saying that this tangent right here, if you have a second order equation, it would be twice. 2 times this diagonal here, which is simply x n. So that equals n times x to the n minus 1. Pretty cool. And in our previous videos, we've shown that the sine area S of the diag of the d of x to the n, well, that equals x to the n, right? We've shown that. And similarly, the d, which is the tangent slope of the signed area of x to the n, well, that equals x to the n. You're back to the same function. They're inverse. They undo each other. Think of it as inverse operators. Like a dump truck, let's say. The dump truck dumps dirt, and a bulldozer digs dirt out. Well, if you do an operation that's called a dump followed by dig, well, you'll end up where you were before. How about if you do a dig and then you do a dump? So you dig a hole and then you fill it, you dump it. So you end up where you started from. That's an inverse operation. That's how you think of these things. That's what the box operators do for you. So, okay. I thought we'd just touch base on that. So, a little bit of trivia I needed to put. So, okay, remember, before there was calculus,
there was quadrature.